Now, what is this diffusion coefficient? This diffusion coefficient is a constant. It's a constant which we get from something called Graham's law. So what is Graham's law? Graham's law. Graham's law is the diffusion coefficient is solubility of that molecule which is going across the membrane, in that membrane, divided by square root of the molecular weight of that molecule. So what does that mean? The more soluble a substance which is going across the membrane is in the bilipid layer, the much more it will go across that membrane. It's simple as that. So if you look at these gases we talk about, O2, CO2, they're highly fat soluble. They can easily cross the membranes. And if you look at it, CO2, it's much more soluble than oxygen in the membranes, almost 20 times more. So it easily crosses the membranes, and because it is lipid soluble. So some substances are more soluble than others. If you look at ionic substances, they're not that soluble in bilipid layers, so the solubility is less. So the constant value, the diffusion coefficient, will be less for that. And when we talk about square root of molecular weight, so think about it. It's in the denominator. That means that the heavier the molecule, the less likely it is to cross the membrane. It's not going to move so much because it's so heavy. And big things don't move so much, heavy things don't move so much, so that could be in the denominator. So that's all what Graham's law is. It helps us to get the diffusion coefficient. Now if we look at facilitated diffusion is the next heading. It's the kind of diffusion where, again, it's a passive diffusion. There's no energy required, things are going along their substance, but now we are involving something called carrier mediated transport. Now what does that mean? So if you look at a carrier, it is a kind of a transporter protein where you have this bilipid layer, phospholipid bilipid layer of the cell membrane, and you have this kind of a structure made of protein which goes across the entire length of this bilipid layer. Now what happens is this molecule is a carrier. What it does is it binds to a certain molecule. There's a certain molecule that can fix in it. There's a special location on it for this molecule to fix in it, and because there are so many more molecules on one side, these will stick to that site, and then eventually this carrier this carrier will just flip to the other side. It does a somersault. So after binding to a certain molecule, so let's just draw this molecule in red which was able to bind to it finally over here. So this carrier protein is eventually going to change its shape, and that special shape, that special location, that binding site has flipped over like this, and now this molecule can go so to the other side. So what I'm saying is it's the same molecule as these other ones, okay? And what happens is, because there are so many more molecules on this side, it is going along the gradient, but it needs a little extra help. Maybe because this molecule is too big, maybe because this molecule has a charge, and charges don't do so well crossing membranes. So for that reason we have these carrier mediated transports, and they're very important in transporting substances from one side to another. Now what is the limitation of carrier mediated transport? It is that there is a limited number of carriers. You can only have so many carrier proteins in one cell. So what could happen is, if you saturate all of the carriers, like you're trying to move one substance from one side of the membrane to another, now what could happen is you have a limited number of carriers, so they can only work at a certain rate per unit time. There's a maximum limit with beyond which they cannot transport. So the flux, the rate of transport is not infinite like in simple diffusion over there, okay? So what happens is you reach a limit, a ceiling of transport, and I'm going to show this in a graph. that compares simple diffusion with facilitated diffusion. Simple diffusion, as you increase the this is the flux, or the rate of diffusion, and this is the concentration gradient. And what happens is, if you increase the concentration gradient for simple diffusion, which I'm drawing in black, it will keep on increasing in a linear fashion. There's no limit over there. But let's just draw facilitated diffusion in red. What happens is, facilitated diffusion, as you increase the concentration gradient, you start saturating the limited number of transporters over there in the cell membrane. But eventually what's going to happen is, things are going to plateau out over here. Now, why does this happen? Why is there a certain plateau that's reached? This is called TM, transport maximum. And this TM happens because you have a limited number of carrier proteins. And I'll give you an example. Imagine you have a big building, a big skyscraper, and you have 3 lifts, and only 3 people can, meaning one person can ride one of those 3 lifts at one time. So it takes 1 minute for that lift to take you all the way up and come back down and take the next person up and down. So you have a building, you have 3 elevators over there, or 3 lifts over there, and it takes 1 minute to go up and come back down over there, dropping the person off over there. So that means that if you have a few people over here, what could happen is, okay, the rate of transport increases, but as the number of people increase even more, then these lifts get saturated. Consider the lifts like the carrier proteins over here. You see what's happening over here? You reach a limit. In this case, it would be 3 people per minute can reach to the top per unit time. 3 people per minute. So this is your carrier mediated transport, which has a limitation of transport maximum over here. So a simple example of this is something with sugar transport, which we can talk about, like GLUT transporters. Edit. What happens is, it reaches the transport maximum, and what's going to happen is, we reach the ceiling and there's no more transport beyond this. Things just slow down after a certain time. Then the other thing you should know about it is, sometimes they can be competitively inhibited. There's something called competitive and also non-competitive inhibition. So what's happening over here? Competitive inhibition is where, let's say you have this this carrier protein. It's got a binding site for a certain molecule, and this molecule I'm going to shade in black over here. Okay, it has to take the substance from one side of the membrane to the other side of the membrane. So it's supposed to flip and take this to the other side. Now, there is another molecule I'm going to draw in red, which looks very similar, which has a very similar structure, but is definitely different. You can see I'm just drawing it a little different, but the shape's complementary. It could bind to that carrier protein over there. So if you put a few of these other chemicals, these red molecules over here on this side of the membrane, there is a chance that you are going to compete for the same binding site. So if this carrier was meant to only transport this black color atom molecule over here, now you put some red molecules, what's going to happen? They're going to take the seats in this bus or in this elevator, and they're going to reduce the rate with which the black molecules are going to cross the membrane over here. So this is your inhibition, and this is competitive inhibition. Non-competitive inhibition is where you use special substances that can bind to this molecule, and that can just stop it from working entirely. There's nothing like, okay, I can just increase the number of black molecules and eventually we'll just knock the red ones out because we're so much more. So the chances of us finding this location by random Brownian motion is much higher. So that's what competitive versus non-competitive inhibition is all about over here. So you can equate this to how we have Michaelis-Menten kinetics for enzyme substrate complex. So Michaelis-Menten kinetics. This is how you'll learn about this in your biochemistry chapters, but it's how enzymes and substrates, there is a rate at which you have this enzyme and this substrate interaction, and the more the substrate you have, the rate increases up to a certain time and all that. So let's not go into that, but you can always say that it follows the enzyme substrate kinetics of Michaelis-Menten. And an example of this is something called the GLUT transporter for facilitated diffusion. So you have these transporters in the basement membrane of your intestinal epithelium, or in your in the basement membrane of your intestinal epithelium, or your proximal convoluted cells over there. So in the nephron. So in the intestines or in your nephron, what happens is you have a special transporter that gets the glucose into the cell. Let's say you ate some sugar for food. Now the glucose makes it into the cell, and that is through a secondary active transport mechanism I'm going to talk about later. But the point is, for the glucose to go from this cell into your blood, into the ECF, that is going to take this transporter. It's going to bind to this transporter. It's going to go into this, and that is how it is. So the glucose enters into the blood over here. This is your GLUT transporter that takes place over there. Okay, you have GLUT1 transporters and GLUT2 transporters. In the upper part of your nephrons, you have GLUT1 transporters, and in the lower part of your nephrons, in the proximal straight tubule, you've got GLUT2 transporters. And we'll again talk about that in some more detail when we reach the chapter on nephrons and sugar transport. Then the next thing is non-ionic diffusion. Here we have a situation where when we have weak acids and bases, weak bases, they have a charge on them, because if you remember, what's an acid? It's a proton donor, and a base is a proton acceptor. So they tend to have a charge on them, and because of this, they can't cross membrane so easily. For that, we have a special kind of transport, which is non-ionic diffusion. So an example of this is ammonia transport. In the GIT and kidneys. So this is one of the main things for non-ionic diffusion, and that's as simple as that. And then we have the active transport, which we are going on to. Next we have the osmosis topic. Osmosis.